This is the physiology of the cells of the nervous system. We have already covered, starting part 2, which is the brain and the spinal cord. Now we are going to start the neuron. I used to do this section first, which is why it's called part 1, but I find I prefer doing it with the larger structures first. So the main cell of the central nervous system is called the neuron. The neuron is a very odd shaped and odd looking cell. It's very specialized. Here we have the anatomy of the neuron. This is the body of the neuron with its nucleus. These sprigs coming off the body are called dendrites. The incoming signals come in through the dendrites. Signals then transmit down this long arm structure called an axon and go down into the axon terminals or synaptic bulbs. These are the synaptic bulbs. This is the end of the axon terminal where we have vesicles full of neurotransmitter that when the signal or action potential comes down into the synaptic bulb, the neurotransmitter is dumped into this cleft between a dendrite of the next neuron called the postsynaptic neuron. The neurotransmitters bind to the postsynaptic neuron, causing another action potential here in the dendrite of the next neuron. So action potential causes a release of neurotransmitter from the vesicles that go across the cleft and bind to the postsynaptic neuron or the dendrite of the next neuron. There are 10 to 30,000 incoming signals or connections from the dendrites into the nerve cell body. The neuron relies on energy with glucose, requires constant supply of oxygen, and requires a constant stimulation of signals coming in from the dendrites. We will see shortly that this signal or action potential, neuronal action potential, involves sodium and potassium ions flooding across the membrane of the axon. There are gates called sodium and potassium gates that will open and close to allow sodium and potassium to flood in and out of the cell, creating a propagation of ions down the axon, which is called an action potential that will then release the neurotransmitters at the end of the terminal end of the neuron. There are other cells of the nervous system that we call glial cells. Glial cells are used to support the cells of the neuron. We have Schwann, the cells should be with a C. Schwann cells and oligodendrocytes. They form the sheath that goes around the axon that we call myelin. This is the myelin sheath formed by Schwann cells and oligodendrocytes. These cells, or glial cells, are connective tissue. The neuron is not connective tissue. We also have astrocytes. Glial cells are the support cells. They feed the cells. They block oxygen from damaging the neuron. They provide the membrane layer of the myelin around the axon sheath. There is a barrier called the blood-brain barrier, which protects the neuron from blood or too much oxygen. This is a protective mechanism for the neuron. Many medications cannot cross the blood-brain barrier that is created by glial cells. So to understand how signals are propagated down the axon, you first have to understand that all cells have a charge across the membrane of the cell. Neurons are charged approximately negative 70 millivolts, meaning that there are more negative charges inside the neuron than there are positive charges on the outside of the neuron. The reason there are more negative charges are as follows. We have negatively charged proteins that exist inside this axon. So we are here inside the nerve cell body and in the axon. We have more negatively charged proteins, but we also have sodium and potassium ions. So we have potassium ions and we have sodium ions. In a normal state after repolarization or resting, we have more ions on one side versus the other side of the membrane. Here we see the inside of an axon that shows resting, action potential, repolarization, and back to resting again. So here we have 3 sodiums to 2 potassiums, meaning that we have more positively charged ions on the outside than we do on the inside. Therefore, this is negatively charged. What is going to occur is when incoming signals coming down the dendrites that are positively charged reach a threshold of above negative 50 millivolts from negative 70, are going to cause an opening of gates that exist in the membrane. These gates open up, flooding the inside of the cell with positive charges. This is going to cause a wave of charges to go down and flood the axon. Here we see resting potential of negative 70 millivolts. This is caused again by 3 sodiums on the outside to 2 potassiums on the inside. When we have a threshold of negative 55 charges coming in from the dendrites from the cell, those sodium-potassium gates will open up, flooding sodium inside the cell. Then we have pumps that will pump them back down. It will hyperpolarize and go back to the resting state. Here we see potassium and sodium being repumped in to the right spots, and then we have a normal resting potential. So we have sodium and potassium gates, and we have sodium and potassium pumps. In the action potential, we have resting potential, depolarization, repolarization, and back to resting potential. Think of the sodium-potassium pumps as a sub-pump, always reestablishing normal resting potential. What the nodes of Ranvier allow us to do is skip sections of the axon. So instead of propagating very small sections, we are propagating large sections. The nodes of Ranvier are gaps between the myelin sheath. Myelin is the insulation along the axon.